All right, hello. I'm going to be doing a recording of a presentation of the nature of waves, and you can use this for sections 1 and section 2 to kind of help you figure out what's important on the notes. So the title again is Nature of Waves. First thing we want to know about waves is the definition of waves. A wave is a repeating disturbance that transfers energy through matter and space. The great thing about waves is that they work not only in water, but also in air, and we'll talk about that later. Second thing about waves is that they transmit energy. When objects with kinetic energy contact molecules, some of that energy is transferred into the molecules. This causes the molecules to move, which passes the energy from molecule to molecule. So think of tossing a rock into a pond. When a rock has kinetic energy, it splashes into the water, and some of that water is moved because of the kinetic energy of the rock. And, as a kid, you can sometimes try all kinds of different which rock gets the biggest splash, and most of you should know that is the largest rock because it has more kinetic energy, and that larger rock will cause more waves. Second thing about waves is that waves carry energy without transporting matter from place to place. A lot of times we think about waves like a wave moves when, say, the rock, but the water actually moves very little. And so energy moves, but the matter that transports that wave doesn't move very much. Okay? So as you can see with this little diagram or graphic right here, it shows how waves move through the water. And you'll notice at this location, at the very top, the water molecule here moves quite a bit, but it moves in a circular pattern. It would move back and forth. Um, if we watched it like, say, something bobbing in the ocean, it looks like the wave is passing the buoy as it goes on. And then farther down, you'll notice that the water moves very little with the disturbance of the wave. Only the water at the very top is disturbed is with a greater amount of displacement. Waves only travel as long as they have the energy to carry, right? If there's no more energy, which is why waves eventually die out, you toss that small pebble into the pond, eventually the waves, the ripples kind of die out because there's not very much energy, and a little bit of energy is lost as it's transferred to the molecules of water as that wave energy passes through. So as a wave moves, some energy is lost to the surrounding molecules. And waves are produced by vibrations or rhythmic motions, which is how the waves of our voice work. We have rhythmic motions done in our voice box and our vocal cords, and that produces sound waves. Here's a picture of a guy producing waves. It's a rope exercise, and you watch the rhythmic motion of his arms, okay, and that is producing different types of waves. Mechanical waves. The thing about mechanical waves, we call them mechanical is because they move through something. And that what they move through is called a medium, matter through which a wave travels. So whatever it goes through, water, air, rocks, it doesn't matter. Whatever is being traveled through is the medium. Okay. A mechanical wave is a wave that can only travel through matter, which is why you don't hear anything in space. There's no matter for waves, mechanical waves, to go through. There are two kinds of mechanical waves. One is a transverse wave. A transverse wave is basically that red block moving up and down, all right, and it's causing waves. This is a typical water wave and things that we see. We call those transverse waves. Second kind is a longitudinal wave. Think a slinky, and then as you're shaking the slinky back and forth, the compressions that you see there, those are longitudinal waves. So we have two different types of waves. Also, longitudinal waves are known as compression waves. Okay. Next, sound waves are longitudinal waves. The air molecules are compressing, as you can see by this graphic here. Uh, there is a compression at the introduction, beginning of this graphic, and then the sound passes through the air molecules. Right. Seismic waves are also longitudinal waves and transverse waves. They have both. And of course, I get a warning. A seismic wave, basically earthquakes, they are both transverse and longitudinal, and you can see by the two graphics down there. The S wave is the wave that shakes up and down, right? And then you have the P wave, or the pressure wave, which is why it's called the P wave, and it is the longitudinal part of the earthquake. Parts of a transverse wave. So let's talk about some wave properties. Let's talk about what the different types of things that I'm interested in for you to know about a wave. So a crest is a high point. The highest point of the wave on a transverse wave is called the crest, and the lowest point is the trough. So right here we have a little graphic that shows crests and troughs. Longitudinal wave, they don't have crests and troughs. We call them compressions and rarefactions. So a compression obviously is where it's compressed, and a rarefaction is where it is stretched out. All right. The way I remember that is the springs are more rare. There's not as many springs in a rarefaction, or the less dense region. Right. Some more properties is the wavelength. All right. A wavelength is the distance between one point on a wave and the nearest point just like it. Frequency. The frequency is how many wavelengths pass a point in 1 second. All right. And a period is how long it takes for one wavelength to pass a point. Okay. So as frequency increases, so the more frequency you have, right, the number of wavelengths that takes to pass a point, right, the period will decrease, okay, which is the amount of time it takes one wavelength. So it's looking at the same the wavelength, but it's looking at it from a different perspective. One, the frequency is how many you're passing through in a second, and the period is what part of that wavelength it takes to pass through that same point. Okay? So amplitude is a measure of size of the disturbance of a wave. And I have a graphic here that's coming up that will show you all this stuff to you. All right, so notice at the very top we have our time, the 1 second time, okay, up here. This is the 1 second, so that's our period. Okay. Now notice we have a wavelength. It's this one identical part of the wave to the next identical part of the wave. The easiest way to do wavelengths is either to use the crests or the troughs, or even you can do the middle sometimes to do a wavelength. You just make sure you're going to the same point of the wave. Okay. Amplitude is how much disturbance you have above the midpoint. All right. And so it's not the total distance between the crest and the trough. It's half of the distance. Okay. Amplitude is how much disturbance you have. If there was no wave, the water would be resting on this dotted line. Okay, and that is time. So notice we right now have 1.5 wavelengths. Okay, going through this time, this period. All right. Okay. How do we calculate wave speed? All right. Well, the speed of a wave depends on the medium through which it travels. Okay, the more solid the medium, the faster the wave will travel. But wave speed, frequency, and wavelength are all related. Okay, so remember, wavelength is how far apart a wave is. The frequency is how many of it is going through at a time, right? And speed is what we're looking at with wavelength and frequency. So here's our equation. Wave speed equation. Wave speed is denoted by v, velocity. We have the wavelength, all right, and we have f for frequency. The theta there is for wavelength, all right. So it's just wavelength times frequency gives you the speed. How many waves are there, and what's their frequency passing, like how long, how far apart they are, multiplied by how many are passing through at a given point. Sorry, I apologize, not theta, but lambda. All right, lambda. Should have looked ahead. All right. What is the wavelength of a wave that is traveling at 343 meters per second and has a frequency of 440 hertz? So we would look at switching a few variables around. We have the wave speed and we have the frequency. So if we were to divide both sides by f, all right, so v divided by f would then give us wavelength, because 2f's would cancel out on the right side. So velocity divided by frequency, all right, 343 divided by 440, give us the answer. All right, thank you for watching, and hopefully that helped out. Anybody that has any questions, let me know. and we'll go from there. Thanks, and have a great day.